Hi, I'm Rolf Schmid, architect for IP transport networks at Swisscom. In this presentation, I will speak about Swisscom's new IP network named Titan for Terabit IP transport and aggregation network. Titan is Swisscom's new converged IP transport platform, which will eventually replace the many IP networks we currently have at Swisscom. Titan is also a greenfield SRv6 microSID based network. So let me start by explaining the Titan vision. Why does Swisscom need a new IP transport network? In this figure, you see Swisscom's network environment back in 2020. I don't expect you to be able to read anything in this figure. I only want to make my point that our network landscape was very complex. We counted 17 different IP networks from 4 different suppliers. Some of the networks were metro networks, others were in the core or data center domain. They were all very specialized, let's say optimized for a single purpose, like for mobile backhauling, for enterprise services, for residential services, like or for TV distribution, or for voice interconnection. And all those networks were MPLS based and interconnected. Developing and operating such a complex environment is very difficult and expensive. It further required specialized engineers for many different suppliers and platforms, which is very difficult in this time of constant pressure on workforce and cost reduction. But these were not the only pain points we had with this network environment. Troubleshooting became more and more of a problem because nobody was able to have an end-to-end view for all of the services, and this impacted stability. We had some outages of critical services like emergency calls, and that had a very negative impact on Swisscom's reputation. Scalability was also a problem. At some point in time, we run into MPLS label scale issues. We could solve this problem, but still we think that scalability is a major concern in the future. The management of these networks was very traditional. Most was CLI based and automation was poor and mainly done by scripting. Monitoring was focused on resources and very basic. Introducing modern management concepts like network analytics and service monitoring, even automation, proved to be very time consuming and very difficult in such a heterogeneous environment. This is why we developed the Titan Vision 2026. The Titan Vision is about simplification, standardization, and automation. And this will help Swisscom to stabilize the network services and reduce the costs. Consolidation is one of the key objectives for Titan. We would like to have a single IP transport network from one partner, which is Cisco, run by one organization, and of course a very small hardware portfolio. We also chose a technology that we think helps us with simplification and scalability, and that is SRv6. I think SRv6 is the most simple and the most scalable service provider technology that is available today. Standardization is also very important in Titan. Standardization is a precondition for automation. So we want to move away from the very customized services we had in the past to standardized general purpose transport services that can be automated. We plan to offer layer 2 and layer 3 VPN and a multicast service for TV distribution. All services should be fully automated, so they should be ordered and managed through an API. We call this network as a service. And all the services should be automatically deployed without any human interaction. Last but not least, we intend to make full use of state-of-the-art telemetry and monitoring. This slide shows the Titan network reference architecture. Titan is deployed in all of the Swisscom locations. First of all in the cell sites, then at central offices, at backbone offices, and of course in the data center. So Titan interconnects our customers in the access to our services in the data center, or of course to the internet or to some wholesale ISPs. In Titan, we distinguish between two types of routers. First of all, we have the service edge routers shown in light blue. These routers actually implement the services. So if I say service, it's a layer 3 or layer 2 VPN service. We will have up to 15,000 such routers at different locations. We have them at cell sites, at central offices, in the backbone office, and of course in the data center. Then, shown in dark blue, these are the so-called aggregators. They are service agnostic. All they do is aggregate on SRv6 the traffic. The metro networks in Titan, they interconnect the central offices to the backbone office in a certain region. We have 15 such metro networks. The 20 backbone offices, they are connected to the data center over the Titan core. And as you can see, we have a very special implementation here. We have two colors, green and orange, and this represents two core planes. And I'm going to explain to you in a minute what this means. What you can see on this slide as well, that's shown in red, is the internet core, which is separate from Titan. So we have some CDNs which are distributed in Switzerland in 20 backbone offices. And we have an internet core network that actually connects to the internet. On this slide, I would like to discuss some of the design choices we took at an early stage of Titan. As mentioned before, Titan is a new greenfield network. So why not use the most advanced service provider technology available? That's SRv6 and microSID in our opinion. What are the advantages of this technology? First of all, its simplicity. All you need is IPv6, ISIS as your IGP, and BGP to build the services. There's no more need for other protocols like LDP, BGP-LU for scaling, RSVP for traffic engineering, and so on. A second advantage is scalability. Segment identifiers or IPv6 addresses are not labels. And IPv6 addresses can, as we all know, be aggregated. And this really helps keeping your routing tables small and IGP convergence fast. Fast convergence in any kind of topology is further enabled by TI-LFA. When we started Titan 3 years ago, the technology was not fully standardized. Today this is different. The technology reached a state of maturity. Almost everything is an RFC and implemented by various other vendors. Interoperability tests show that deploying an SRv6 multi-vendor solution is feasible today and there's no vendor lock-in anymore. We further decided to go with fixed chassis router rather than modular routers. In our legacy networks, we deployed large modular routers with high internal complexity, rather poor port density, and a huge power consumption. When we started with Titan, fixed chassis routers with high performance became available, which offered sufficient capacity for us to be used as core and aggregation routers. I have to admit we are in a sweet spot here because Switzerland is a rather small country. What are the advantages of fixed chassis routers, also known as router on a chip? First of all, it's reduced complexity in hardware and software, and this helps you to get higher availability. Then, of course, since the traffic only has to go across a single ASIC, you will also get the lowest possible latency. And then such systems are rather small and have a very small power consumption. And what I also like about fixed chassis routers is that they usually have a clean failure. So they either work or they don't. But there's only a small chance that you have a half broken router. SRv6 supports traffic engineering out of the box. And of course, we decided to use it. We started with the implementation of 3 routing topologies for our services. The default topology is ECMP load balanced. Then there are other topologies we support, like a low latency topology. The low latency topology is used for delay sensitive services such as mobile backhauling, for example. We implemented the low latency routing with flex algo low latency and with dynamic two-way delay measurement. Then we also implemented what we call a disjoint path service, and this builds on 2 single plane services. So a single plane service is using only one of the 2 core planes in Titan. And we achieved this with segment routing traffic engineering. So we set the first SID in the segment list to an anycast SID, which directs the traffic to one of the 2 core planes. Switzerland is a banking country, as you know. We have customers mainly in the financial sector that require traffic encryption. Therefore, we decided to use MACsec encryption on core and edge links in Titan. So far, we are not encrypting the traffic in the metro network because there is currently no need for this, and we already use IPsec encryption for mobile backhauling. Our metro networks are quite different in size, and it is difficult to find a one-size-fits-all hardware solution for certain routers. In the past, we either deployed a very large router that meets the scaling requirement of the largest metro, but was an overkill for all the others, or we deployed different chassis sizes, which does not really help to keep our portfolio small. In Titan, we decided to use a scale-out approach for the metro networks. So what do? We split large metros into smaller submetros, and each of these submetro can be accommodated by a single fixed chassis router. So say a small metro like Chur will have a single router, a single fixed chassis router, and larger metros such as Zurich is split into 3 or 4 submetros, each with one of those fixed size chassis. Last but not least, we evaluated the potential of routed optical networks, that is coherent ZR+ optics in the routers. Here I have to mention that Swisscom has just finished the rollout of a modern OTN network with 400 gig services, managed path diversity, and optical protection. We did a business case for using ZR+ optics in our core network as alien wavelength on our OTN network. There are 2 reasons why we decided against it. First of all, the savings were only small. This might be different in your case, but for us, the savings were small. And then our internal organization was not yet ready for IP optical convergence. Accepting alien wavelengths from routers was a clear no-go for the optical transport department. However, in Titan, we still do deploy ZR+ optics, but we only use it for 400 gig links over dark fiber, where distances are in the range between 10 to 50 kilometers. So ZR+ optics on dark fiber, but no ZR+ optics on the OTN system so far. Let's have a look at the Titan network deployment. First of all, the core network. It was launched in mid-2023. On this picture you can see Switzerland. You can also see the data center locations, or our data center locations in Switzerland. Our core network interconnects the data center locations. So we deployed core routers in each data center. As core router, we used the Cisco 8202 routers with the 32 times 400 gig ports and MACsec support. Those core routers were partially meshed, as you can see in the picture. So each of the green lines is a core link with 800 gig. This is 2 times 400 gig for the time being. What you can also see in this picture is that there is no single point of failure in this core network. But, however, this was not good enough for Swisscom. So why is that? In order to understand this, you have to know that Switzerland is a high-quality telecom market. Our customers, they are willing to pay a price premium to get superior quality, which includes availability. And this is where our internal business units were concerned. They said a single IP networks, although without a single point of failure, will not be available enough for our customers. You have to do something to increase the availability of this core network. So what did we do? We basically copied what we already have, what is shown in green in this picture, and we kind of duplicated everything. So we created a second core plane. You can see it here. So we started calling this the green core plane that was shown before, and an orange core plane. There are two totally independent core planes carrying all the traffic. The two core planes, they are each fully redundant by itself, and the planes are not linked by an IGP. So it looks like two separate core networks. However, they share the same hardware type, and still today they use the same software release. In the future, we would like to introduce separate software releases for the two planes, but this is not possible today because we always need to roll out the latest feature release. So how do the services use the two different core planes? So each of the services, if it uses a default routing, is sent over both core planes. So this is a per flow load balancing across the two planes. Of course, as mentioned before, you can also get a single plane service. If you want to build a disjoint path service, you use two of them. So you can send some traffic on only the green plane while the other traffic is only using the orange plane. So that's how you achieve disjoint path service. Then this is how we connect the data center to the Titan core network. We show here the case of Zurich, where we have two data centers. Of course, in the data centers, we have several data center service edge routers that need to be connected to the Titan core. And we do this by introducing an additional aggregation layer. So we call these the data center aggregators, or DAGs. Data center aggregators, they're the same hardware type as the core routers. And we dual home each of the data center service edges by 100 gig to both of these data center aggregators. So there's always a local orange and a local green data center aggregator, which allows a service edge router to load balance the traffic across the two core planes as discussed before. We further deploy in each of the data centers a data center route reflector. That's also a Cisco router, Cisco ASR 9902. Last but not least, let's have a look at how we connect the access to the Titan core network. In this example, we focus on a metro network in Chur, which is an alpine region. Of course, we have different metro networks in Switzerland. We have like 10 metro networks. If you count the sub-metro networks that I mentioned before, we have 15. So let's focus on the metro network in Chur and on a central office. Let's take the one in Davos. In each of the central offices, we have a lot of different devices that need to be aggregated. First, we have the access platforms. access platforms for both copper and fiber, and of course PON as well. And then we also deploy in every central office B2B access service edge, and of course a cell-side router for mobile. And there are even further cell-side routers out in the field, not located in the central offices. And they all need to be aggregated somehow and connected to Titan. For this purpose, we deploy an access aggregator or two access aggregators. So all the devices in a central office, they get dual homed to two access aggregators, and the two access aggregators, again Cisco devices, they will be linked by 100 gig uplinks to what we call the metro aggregators. Now the metro aggregators, they are located in the so-called backbone offices. We have two backbone offices in every metro or sub-metro. Again, we use the same hardware type for the metro aggregators as for the data center aggregators and core routers. And we connect the metro aggregators to a core router in the same plane. So again, we have an orange metro aggregator, which is going to be connected to the orange core plane, and the green metro aggregator that is going to be connected to the green core plane. We also deploy metro service edges in the BBOs. They are used for service termination in the BBO. Let's take, for example, B2C service from an end customer which goes to a BNG which is located in the BBO, or let's take, for example, mobile backhauling which is terminated again in the BBO because that's the location where the IPsec tunnel termination is. We've only just started deploying our metro networks, so we started doing the rollout in end of this year, and we think that we will be able to finish this by mid 2025. So far I covered the physical topology of the Titan network, so let's have a look now at the logical topology, which is routing and addressing. And this is where the true beauty of SRv6 is shown, which is address summarization. First, let's have a look at our addressing concept for microSID locators. So we allocate a /28 from the ULA, which is the unique local address space. So let's assume we allocate the FDCA FE00/28 from EULA. After this prefix, we use 4 bits for flex algos. So this allows us to have 16 flex algos, followed by 8-bit, shown as DD here, for a domain ID, and then again followed by 8 bits of node ID. So this is your /48 locator. Now we can have 256 nodes in each domain. We can have 224 domain in each flex algo, and we can have a total of 16 flex algo. And it is now easy to do a summary. We can either summarize by domain, as shown here. This will be a /40 summary, or we can also summarize, say, per flex algo, which is a /32 summary. So let's see how we do the routing and the summarization. In this picture, you see the data center in Zurich on the right side, the core in the middle, and the metro, like the metro in Geneva, on the left side. In between the routing domains, there are metro aggregators and data center aggregators, and they act as area border routers. All the routing domains are ISIS level 2, and we do summarization and redistribution from metro to core and vice versa, as well as from data center to core and vice versa. So how does this work? Let's assume that for a data center in Zurich, we allocated a domain ID, which in this case is CC. So a data center service edge in Zurich will get the locator FDCA FE00 CC33, for example, Another one would get CC15/48, for example. And all those locators, they can be summarized now by the data center aggregator with a domain summary. And the domain summary is a /40. In this case, it's the FDCA FE00 CC00/40. And this is the summary for all of the locators in the data center in Zurich. The same can be done, of course, on the other side, say in a metro network. The metro network in Geneva is quite big. 256 nodes, node IDs will not be enough. We need more than that. So that's why we allocate, say, 2 domain IDs. One of the domain ID is the AA and one is the BB. So one of the access service edges in the Metro Geneva, for example, gets the FDCA FE00 AA11/48 locator, whereas another access service edge gets the FDCA FE00 BB22/48 locator. So they are 2 domains. Now again, the Metro aggregator can summarize per domain. So since we have 2 domains, it will inject 2 summaries into the core. One is the AA00/40 and the other one is the BB00/40. And of course, we can do the same in the opposite direction. That's from the core towards the data center or towards the metro network. Here we can even build larger summaries. We can do /32 summaries. So the metro aggregator and the data center aggregator, they will only inject the FDCA FE00/32 into the data center and the metro networks. So which locators do we see in each of the routing domains? Of course, in the core domain, we see the core locators, and we only see /42 locator summaries for all the metros and the data centers. And then in the metro and in the data centers, we see a single /32 that represents all the other data center and metro networks and the core networks, and of course the local locators as well. This is a drastic reduction of prefixes in your ISIS routing table, and this really reduces the convergence time of your network. That's really something I like about the SRv6 technology. But there are also some disadvantages of summarization. One of the problems is that summarization can interfere with fast convergence. In the past, you were triggering your fast convergence like the pick edge on the disappearance of a remote loopback address. So take, for example, a router in the Metro Geneva could detect if a router in the data center Zurich was going down because the loopback address of this router, this host address of the router disappeared, and then the access service edge in the Metro Geneva could trigger fast reroute. Now this is not possible anymore because the routers in the Metro Geneva, they will never see a /48 of any data center service edge of the data center Zurich, because all those locators, they are hidden in a summary, and the summary will still be advertised to Geneva because other data center service edges are still alive. So how would you trigger your fast convergence now? Of course, there is a solution for this problem. It's called UPA, Unreachable Prefix Announcement. What is UPA and how does it work? So usually the data center aggregator would advertise a /40 aggregate towards the core, and the MAG would then advertise a /32 towards the metro in Geneva. Now, if the data center service edge goes down, the data center aggregator would notice that it goes down and would then poison the route to this individual locator. So it would send or it would advertise this prefix, the CC33/48, with an unreachable ISIS metric. the unreachable ISIS metric is a basic functionality of ISIS. It's already standardized and you don't have to ask for a special feature from your supplier. So this will work with any standard compliant ISIS implementation. So the DIG would not only send the summary, but will also send a Poisson/48 route for this data center service edge router. And this will also be propagated inside the metro. So the access service edges, they will get the standard /32 aggregate, but they will also get a poisoned route, a Poisson/48 route for the DSC that actually failed. And they can use this information now to trigger fast convergence to another remote egress point. But there are still some corner cases to be aware of. So UPA really helps you with a lot of things, but it does not really help you if at the same time with your failed remote router you have a partitioned ISIS area. And this might lead to black holing situation in your network. Again, there is a feature available from Cisco to overcome this problem, and this is called the ISIS partition detection. I think it's supported from iOS XR 7.10 on. ISIS partition detection is able to detect partitioning of your ISIS domain, and if it detects such a partitioning, it will replace the summary routes advertised by your area border router by more specific routes to overcome this problem. So again, I believe that address summarization is really one of the key advantages of SRv6, and we have all the features available to make this works in any situation. On this slide, I show you the overall Titan roadmap. The Titan strategy was defined back in 2020, and this was followed by a partner selection. We did a tender with several potential partners, and in the end, we selected Cisco as our technology partner for the Titan network. After that, of course, we started doing architecture and roadmap work. We started doing the core and the data center networks first. This was mainly engineered and rolled out in 22. So the core network became alive in spring 23 and the data center network shortly after. Now we are focusing more on the metro networks. We started rolling out metro network components, but there's no metro network live so far. I think it will become live at the beginning of 2025. And then it will take 1 year or more than 1 year to roll out and power up all the metro networks. That's a large effort because, as I said, we have 15 metro networks. We have over 900 locations where we need to deploy routers and take them into service. In parallel to all the development activities, we do a lot of automation as well. So a lot of development with automation. We introduced a CI/CD pipeline. We introduced a new way of configuring our routers with NSO. There's also a new assurance approach and so on. So there's a lot of IT related development going on, and this not really makes us any faster. Then, of course, we have to do a lot of service migrations. All the services today, they run on legacy networks. We have to migrate all the services to the new Greenfield Titan network. We already did this successfully for VoIP interconnection, so voice over IP interconnection service. This is a rather small service. There's not that much traffic, but it's very important traffic because it's voice traffic. And I mentioned before that we had problems with emergency calls. So the reason why we did the VoIP interconnect service as the first service was that we had lifecycle issues with the legacy platform. After that, we replaced our mobile core network. That was also done successfully in 2024. Next year, we do a lot of different migrations in parallel. So we will migrate the mobile metro network, the B2C metro network, and the B2B network at the same time. And then this is followed by the migration of the various core networks that we still have. Shown on this figure is that everything should be migrated by end of 2026. This is going to be difficult, I think. There's a lot of work that needs to be done, so it might take us a little bit longer. So you see the whole journey from where we decided to go with Titan to do something new, to do a greenfield approach until we have everything migrated takes at least 7 years. So we have a lot of migrations to do in the upcoming years. And this slide is about how we do the migration. What are the objectives of our migrations? First of all, we would like to have the smallest possible service impact, of course. Our customers should not be able to see that we actually migrate them. We also need to optimize all those migrations for sensible resource usage. We would like to limit the number of on-site intervention and the number of night shifts as much as possible. And this, of course, requires that we have a highly automated migration procedure. We want to be able to do the migration stepwise, and it should also be designed for quick rollbacks should something go wrong. And then, of course, we have to coordinate all those migrations with the customer. And we, and as well as the customer, will always monitor those services constantly during the migration so that we can see if something goes wrong. So here is the generic migration approach we are using. On the left side, you see the legacy MPLS network with its PE routers and some connected CE routers. On the right side, you see the Titan network, SRv6 based. So first thing we need to do is to somehow connect the Titan network to the legacy network. This can be done in several different ways. I show 3 possibilities later on. Then we have to extend the service. In this case, it's a layer 3 VPN service running in the legacy network. We have to extend this service over the interconnection that we just built to the Titan network. So we extend the layer 3 VPN to Titan. After that, we can move CE by CE. We can move the services from the legacy network to the Titan network. If this was a service with a single access, of course, it would have a service impact for this single access because here we need to do repatching. If it was a redundant access for a service, we can do one leg by one leg, and therefore there would not be a service impact for that customer. And then after we moved all the CE routers from the legacy network to the Titan network, we can disable the customer layer 3 VPN in the legacy network. And once all the layer 3 VPN in the legacy networks are gone, we can start dismantling the PE and core routers of the legacy network. And here are 3 possible migration strategies. So these are the ways on how we interconnect the Titan network to the legacy network. First of all, there is option A. So we can connect the MPLS PE routers to an SRv6 PE router, and then between the 2 PEs we have eBGP running on separate VLANs. So that's a normal like option A, inter-AS option A peering between 2 PE routers. So that's one way of interconnecting the 2 services. Another way of interconnecting the 2 services is the dual connected PE. So if you have a modern PE, a modern MPLS PE, it could probably speak SRv6 as well. So you can dual home this PE route to both the MPLS network and the SRv6 network on 2 separate interfaces. So such a router can then communicate with CE routers that are reachable through the MPLS network and with CE routers which are reachable through the Titan SRv6 network. It can, however, not be a transit router in this case. We use option A mainly if you only have few and infrastructure type of VPNs, or if the PE router does not support SRv6. If the PE router supports SRv6, or if we have a lot of services to migrate, then we usually use the dual connected PE approach. There is a third approach that we have not been used so far. It's the interworking gateway. You can also put a router in between the Titan and the legacy network that on one side speaks SRv6 and the other side it speaks MPLS, and it can do the translation between the two worlds. So this device could then be transit between legacy network and Titan. But so far we've never used this and we don't have any plans to do so in the near future. I already explained about the Titan network topology with the two independent core planes, and that each plane is fully redundant by itself. I also explained that traffic between two endpoints is usually ECMP load balanced over all the available best paths. In the Titan network, we have many active paths between two endpoints. In the figure shown in the top part, I show the active paths for traffic between an MSC in Geneva and a DSC in Zurich. You can easily identify 4 active paths, 2 in each of the 2 core planes. If you consider that each core link is a bundle link of 2 400 gig links, you end up with a total of 64 different paths a packet can take from left to right. Now, of course, it would be great if we could monitor the performance of all those paths. At Swisscom, we do have some experience with path performance monitoring. For example, for the quality reporting for enterprise services, we used in the past IP SLA and connectivity fault management. Both technologies rely on probing traffic that is generated by the CPU of the network elements, and therefore the solution does not scale well. Another disadvantage is that probing is not ECMP aware, meaning that the probing traffic will always take the same path. Another example is mobile backhauling, which is latency sensitive and where we used latency monitoring with external stamp appliances. The stamp appliances are connected to the network at the BBO sites, and they constantly measure the latency to the mobile base stations. This solution scales quite well, but you need to deploy and manage the external appliances, and again, such a solution is not ECMP aware. A solution which might become interesting in the future is IOAM, in situ OAM. With IOAM, you do not rely on synthetic probing traffic anymore, so no more traffic generated by the network element. Instead, you embed your telemetry data in the user traffic. On-pass delay measurement with postcard modes and IPFix export could be such a solution. Swisscom is active in the IETF to define related standards. However, it is not clear if such a solution is going to be implemented by the major network equipment vendors. Currently, it is not available on the Titan routers. So, is there a solution that is scalable enough and feasible to be implemented in Titan? In my opinion, yes. The Cisco Integrated Performance Management, IPM, looks promising. Why that? IPM is an active probing mechanism. It is fully integrated in the Silicon One ASICs, so not executed by the CPU, and it scales extremely well. It can send, receive, and collect the information of 14 million packets per second. That's a lot. Then IPM is ECMP aware and capable of measuring performance on all of the active paths. IPM is based on standard STAMP and can measure the 3 L's of your traffic, that is latency, loss, and liveness of each path. We already did a POC of the Cisco IPM technology in our lab environment. It looked quite promising. As there was not much interesting data to be collected in a lab environment, we are going to do a trial in the Titan production network as a next step. On my last slide, I would like to quickly mention our ongoing design work. So far we implemented layer 3 VPN services only. Now we are working on the design and implementation of layer 2 VPN, EVPN services. We use such services as carrier Ethernet services for enterprise and wholesale customers, and for backhauling of the residential access nodes to the BNG in the metro networks. The main work here is on modeling and implementation in our IT system, because, as I mentioned before, service fulfillment and assurance should be fully automated in Titan. Scaling of the layer 2 VPNs on the different service edge routers is an important factor as well, and we started a discussion with Cisco on advanced scaling features. Then we have to connect a large number of virtual PEs to the Titan network. We use those virtual PEs for our SD-WAN solution. The challenge here is the limited feature support on the virtual PEs that we are using, which makes it a bit difficult to meet our scalability and fast convergence requirements. To be able to troubleshoot problems of our customers, we further require a port mirroring solution that is fully integrated with SRv6. We would like to mirror incoming customer traffic into an EVPN E-line service, and this service should transport the packet to a centralized traffic analyzer. This could be a SRv6 DX2 service, for example. We are discussing such a feature with Cisco. Then multicast is still very important for our residential customers. We still have a lot of TV users connected to our network. The current multicast distribution solution is based on PIM and IPv4, and we've been using this for almost 20 years now, and it works quite well. Now, of course, it would be nice to have a more modern solution that is based on SRv6, like uSID, for example, or at least IPv6. However, there is no such solution available today. And moreover, it would be a big effort to replace the current PIM IPv4 solution with a new technology. It requires a lot of development work on the server and set-top box side of the Swisscom TV solution, and then we would also have to convince our wholesale customers to do the same on their side, and that is a bit difficult. So we decided to implement the current solution, PIM IPv4, in the Titan network for the time being. This means we run dual stack IPv6, IPv4 in Titan. But we will closely follow the development and reconsider the multicast solution in the future. With this, we have reached the end of my presentation about Titan, Swisscom's new converged IP transport network that is a greenfield, state-of-the-art SRv6 network. Thank you for watching.